Okay, so let's revisit an old problem here. In this problem, before we were looking at a small political sign hanging from our car antenna, and now we're going to do a big political sign because, well, bigger is better. The size of this is 0.5 meter by 1.5 meters, and our car is traveling at 25 meters per second. The roughness on the sign is 0.3 millimeters from printing, and we want to know what the force is on our pole so that we can choose a correctly sized pole. All right, so our Reynolds number is a function of length, and it should be obvious from now, no matter what, you're calculating a Reynolds number. You either need to tell if it's turbulent or not turbulent, or you need it in your drag coefficient correlations. So we're going to calculate our Reynolds number, which is going to be equal to rho u L over mu, which is 1.2 kilograms per meter cubed times 25 meters per second times 1.5 meters divided by 1.6 times 10 to the negative fifth kilograms per meter second. And that's going to give us a Reynolds number of 2.8 times 10 to the sixth. Great. Now, as our friction coefficient chart shows us for a flat plate, we need to know our relative roughness. So let's go down here and calculate our relative roughness. We have 0.0000, nope, that's a 3 there, 3 meters divided by 1.5 meters. Give us a relative roughness of 2.0 times 10 to the negative fourth. Great, so now we go back up to our chart. Let's clear our chart here real quick. Oops, it didn't work. From our last lecture. And we're going to first do our Reynolds number line. So we'll do a line up from our Reynolds number. Our Reynolds number was 2.8 times 10 to the sixth. So that's going to be somewhere around, there's 1, 2 is going to be right about here. So we draw up our Reynolds number line at 2.8 times 10 to the sixth. And then we draw over our line we follow our E over D line. And our E over D line was 2.0 times 10 to the negative fourth, which is actually this line right here. So we follow this line over, and then it kind of goes down and hits it right there. And so we go straight across, and we see that we have a drag coefficient of 0.005. Great. So let's go back here. We know that our CD is equal to 0.005, which is equal to our drag force divided by 1/2 rho u squared times A. So if we want to solve for our drag force, it's just FD times is equal to, 0.0005. Let's write that correctly. 5 times 1/2 rho u squared times A, which is equal to 0.005 times 0.5 times 1.2 kilograms per meter cubed times 25 meters per second squared times 0.5 meters times 1.5 meters. And that gives us a drag force FD equal to 2.92 newtons. Now you'll note that our Reynolds number was not in the completely turbulent region for our E over D values, so we weren't able to use our correlations, right? We weren't able to use any of these formulas we developed in the previous lecture. So we had to use our chart because it was in this no man's land of this region right here. Anywhere in here, you have to use the chart. Anywhere in here, along this line, or this line, we can use our correlations. So we can make this a little bit more complicated. We can not print them and instead use thick reflective stickers, in which case our new E over D value should be equal to 1.5 not E over D, sorry, E over L. 1.5 millimeters divided by 1.5 meters is going to be equal to 1 times 10 to the negative third. So that's our new roughness. So if we go back up to our plot here, and we go to 1 times 10 to the negative third, and follow that over here, we see we are in the completely turbulent region now. Barely, but we're there. So we can use our completely turbulent correlation, and we're going to, just to practice it. So CD is equal to 1.89 minus 1.62 times the log of E over L, all of that raised to the negative 2.5, which is equal to, when we plug in our E over D value, ends up giving us drag coefficient of 8.5 times 10 to the negative third. And we plug that in just like we plugged it in before, and we get an FD is equal to 4.79 newtons, which is twice what we had, well, a little less than twice what we had before. So increasing the roughness had a large effect on increasing our drag force. And the reason is because these large printed numbers or letters on our sign, which would look something like this, cause large eddies, right? They cause turbulence, which is going to raise the turbulence in our flow. And as we know, turbulent flow has a higher shear stress at the surface than non-turbulent flow.